Okay, people, hi again. I'm going to try to tell you how particles interact. I'm trying to go a little bit fast to see if I get this done in less than 15 minutes, which is more or less the limit that I have at the moment. So, go on the videos of the particles and antiparticles and the decays, the beta decay and the positron emission to get some background for this, otherwise you're going to be completely lost. So here we go. Feynman, he's the guy responsible for what we're going to talk about today. He is quite known by getting a Nobel Prize, by playing drums, or by being a womanizer. So what did Feynman did? So first of all, let's think about basic science. So we know that when two objects collide, they exert an equal and an opposite force on each other, Newton's third law, and the momentum is transferred between these two objects. So Feynman said, alright, so then I have an electromagnetic force between two charged particles, and this is due to the exchange of a virtual photon, so photons that cannot be detected directly. And this made this interaction into diagrams. These are called the Feynman diagrams, which is, as is written, the representation of the interaction between two particles or antiparticles, or the decay of a particle or an antiparticle. So let's look at what we have here. PP, PP, so I have protons. So a proton meets another proton. They have here a virtual photon, which is going to be the exchange particle here. They are going to repel each other because they have same charges. So the photon carries on with its life. The proton carries on with its life. The second proton carries on with its life, and they are all happy forever now. So when I have this Feynman diagram, what I need to take in consideration is that the time goes upwards, okay? So this is before the two protons interact. This is after the two protons interact, okay? The actual arrows, they do not represent the path of the particles, okay? So it's just how I do it. And in here, in the middle, so kind of getting this type of shape together, I have the exchange particle. In this case, I have a virtual photon, here it is, because I'm talking about charged particles. You all know about other exchanges particles later on. So these models to explain why particles either attract or repel. So let's look at this diagram first with the blue guy and the green guy. So light charged particles. So I have the thrower, the blue one. He throws a ball to the green guy. Because momentum is conserved, as he throws something forward, he moves backwards, okay? So away from the green guy. So when the thrower recoils, that happens because the ball left his hands or her hands. And then the receiver recoils when they catch the ball because the ball transfers the momentum, so kind of the exchange of the virtual photon, okay, that exchange particle, and they repel from each other. So this guy gets the ball, moves backwards. They are like charges, they repel. Opposite charges, then the analogy is thinking about a boomerang. So the blue guy is now throwing a boomerang to the green guy. And because momentum is conserved, as he throws the boomerang forwards, he goes backwards, getting closer to the green guy. The green guy receives the boomerang, and because moment is transferred, he's going to go and go closer to the blue guy. So they attract each other. And that's what it says in here. So opposite charged particles, the thrower uses a boomerang instead, and the catcher and the thrower attract each other. Now, weak nuclear force, we need to know about the weak nuclear force, but because it's going to be responsible for these decays that we are going to talk about now, okay, for these Feynman diagrams. But just make sure that we do not confuse the weak nuclear force with the strong nuclear force. I'm just giving you here the definition of the strong nuclear force that you got in the very first video, okay, which is called the structure of the atom, I think. So the strong nuclear force is the attractive force between the nucleons, so protons and neutrons, that hold the nucleons, so the protons and the neutrons, together in the nucleus. I said protons and neutrons, right? If I didn't, that's what I was supposed to say for nucleons, okay? A nucleon is how I refer to a proton or a neutron, so something that is inside the nucleus. So the strong nuclear force keeps the protons and the neutrons together, okay, in the nucleus. The weak nuclear force is going to be the force that is responsible for a decay, either a beta decay or a beta plus decay, which is standing for the positron decay. Look at the previous video, which is called Particles and Antiparticles, to see these decays, okay? So this is the beta decay, okay? So this is one, beta minus. I have X gives me Y, and I get a beta particle and an antineutrino. You may remember that this happens because I have too many neutrons and one becomes into a proton, right? So in the nucleus, I'm going to have this beta minus decay to happen because a neutrino, so nothing to do with this antineutrino, is a neutrino that is going to interact with a neutron. Remember that in a beta minus decay, I have too many neutrons, and it's going to make the neutron change it into a proton, okay? So when I get a beta minus decay, I get too many neutrons, the neutron goes into a proton. This happens because of a neutrino. I get an antineutrino. On the other hand, remember that I had in the last video the two decays, one next to each other, for us to make the comparison. So on the other hand, if you understand the beta minus decay, you will understand the beta plus decay really simply as well. So in this case, I have X gives Y plus the positron, the antiparticle of the electron, plus the neutrino. So in the positron decay, I have a nucleus that is too rich in protons, and one of the protons is going to change into a neutron, and I get a neutrino. So why does this happen? So an antineutrino is going to interact with a proton and make it change into a neutron, and therefore I get the beta plus particle and the neutrino, okay? I know that I'm going a little bit too fast, but you can always pause the video. So weak nuclear force is the force that is responsible for these decays in the diagrams. Beta minus, check in the previous video how it happens. The neutrino makes the rich in neutron nucleus to get one neutron to go into a proton. I get an antineutrino. In the positron emission, I have an antineutrino that makes a rich in protons nucleus to have one proton to go into a neutron, and when this happens I get a neutrino, okay? So the W bosons, which are W standing for weak, these are going to be the ones that are going to be responsible for these interactions, okay? So these interactions between the neutrinos and the antineutrinos and the other particles, the neutrons, the protons, they take place because we are exchanging the W bosons. So for charged particles, I exchange the virtual photon. For antineutrinos, neutrinos, and other particles, the kind of the coin that I use, so kind of instead of giving money or the chocolate, so the thing that I exchange to get something else from the other one is going to be the W bosons, so the weak bosons. So W bosons, they are the carrier of the weak nuclear force, so they have the weak nuclear force with them. They have a non-zero rest mass. They can be positive if I have a positron decay, or negative if I have a beta decay. So they have this positive or negative charge, and they have a very short range. So this happens only when things are very close to each other, okay? So their range is about 0.001 FM, which stands for femtometers, which is 10 to the power of minus 15 meters, okay? So again, this was in the very first slide, something like the structure of the atom, or maybe actually it's in the second video, which is the stable and unstable nucleus. Go on the videos and look for it. So Feynman diagrams for these interactions. So I have here my beta decay and my positron emission. In terms of Feynman language, I can say that my beta decay is a neutron-neutrino interaction, because my neutron is going to interact with my neutrino, making my neutron to go into a proton, look at the diagram, and then getting a beta particle being emitted. So this is the representation of this equation in terms of Feynman diagram. I have a beta particle, so beta minus, so I get a W minus boson, okay? Now in the positron decay, so when I have too many protons, one of them goes into a neutron. This is because of an antineutrino. So this is going to be in Feynman language, so in interactions, this is going to be a proton antineutrino interaction. So again, my antineutrino, here we go, the neutrino symbol with a hat, meets the proton, makes the proton change into a N, neutron, okay? And when this happens, I get a particle being emitted, which is, here we go, the positron, beta plus. Again, beta plus, so the W plus, the W boson, the positive one, gave me this interaction to happen, okay? So made it happen. As always, the charge must be conserved, so let's see if this is working, so if this is making sense. If I want to see if my diagrams are correct, I can always think about the charges of the particles. If the charge is not conserved, it means that is wrong and we need to do it again, okay? So charge before the interaction, neutron 0, neutrino 0, so charge before 0. And then after the interaction, proton, positive charge, beta minus charge, so plus and minus, I get 0 overall, sorry. So 0 before, 0 after, charge is conserved. Let's look at the other one. I have a proton, positive charge, meeting an antineutrino, 0 charge. It gives me a neutron, positive charge, and a positron, positive charge. I said positive, this is 0 charge. 0 charge in hand meets the positron, positive charge. So overall, 0 plus, positive charge after, overall plus 0, positive charge before the interaction. So charge is conserved. I'm going to leave here because the next slide is going to be a little bit more complicated and I want to make sure that I'm not running, okay? So I have the continuation of the interactions in the next video because I have other Feynman diagrams. So see you in a bit. Bye!